So, I just recorded a whole entire video where the audio wasn't getting recorded, and that's my bad. Total rookie mistake. I kind of think it was an important video. I think it was good, so I'm going to see if I can kind of salvage it by just talking over it, kind of like overdubbing it. So I wonder what I'm saying right now. You think it was funny? You think it was cool? I bet it was cool. I'm not going to talk till I do something. You guys should probably just fast forward until you start seeing ink show up on the screen anyway. Okay, fine, I'll talk. Um, the plan was to... Oh, I'm doing something. Alright, so what we're talking about is just plotting complex numbers in the plane. And if you had that number 1 plus 2i, then it has a real part. The real part is 1, and it has an imaginary part. The imaginary part is 2. So to graph it, you can see me showing the x-axis. We just let the x-axis be the real axis. And you'd plot the 1 on that part. You'd go over 1. You'd treat it like the x-coordinate of an ordered pair. And the y-axis becomes the imaginary axis. So for us, that part would be 2. So you literally just plot this complex number like the ordered pair 1, 2. And that allows you to visualize complex numbers in a coordinate plane, and you can kind of make some observations about them by visualizing them in this way. And it's pretty simple, in my opinion. So there's that red one. Ooh, back of my neck had an itch. Alright, so to graph this guy, we would obviously do the same deal. We're just going to go left 3, down 4. Because our real part is -3, so that's on the x-axis. Our imaginary part's -4. That's down the y-axis. So left 3, down 4, there's that guy. C equals 4 is all real. It's just only a real part, but that still makes it a complex number, even if you had that plus 0i. That's what I'm saying over here. So we're still a complex number, even if we're purely real. So to plot this, you would just go 4 to the right on the x-axis. Okay, and then obviously that last number there is pure imaginary. It's only the imaginary part. So you just go down the y-axis, 1, 2, 3, there you go. So that part's a piece of cake. So the next thing we wanted to do was take these imaginary numbers in the form of a plus bi, which is called standard form or rectangular form. And we wanted to convert them into a more useful notation. It's more complicated, but it is more useful, trust me. And that new notation is going to be called polar form or trigonometric form. Okay. So taking that complex number, I wonder what I'm talking about right now. Okay, so anyway, if we plotted this number, we would go to the right by A, we'd go up by B, not by I. Scratch that I out. We only go up by B. But that gives us a visualization of our point in the complex plane again. And so if we wanted to convert this to polar, wouldn't we just have to figure out that distance there, which would be our radius? And wouldn't we have to figure out that angle there, which would be theta? Once you've got r and theta, you're in polar form. And so, how did we do this before? Didn't we just imagine this as a vector? Look at me drawing a vector. Look at that light blue vector. Well, that vector has a magnitude, and that vector's magnitude is literally what r is. And we had a formula for magnitude. But here I'm pointing out, here's that same old formula that you probably remember, which is that the radius, which is like the magnitude, would just be our two components, a and b, squared and added together. And our direction angle came from that formula there, right? If you were going to solve for theta, you would do inverse tangent of both sides. And technically you'd be finding phi. So it's the inverse tangent of b over a, and we do the absolute value, because what we're really finding is the reference angle. And then you map it into whatever quadrant you need to be in. But those same formulas that allowed us to turn just ordered pairs into vectors are going to work to turn our standard form complex numbers into polar form complex numbers. Okay, so once you've got that polar form, you don't want to just say r comma theta, like, and express it as a point. You want it to be a number. And again, vectors kind of saves our butts here. If you break this down into components, then wouldn't that green component literally be r cosine theta? That's how we found the horizontal component. And the vertical component would be r sine theta. See, that's what I'm showing you right now. And so that means that our complex number is the sum of those two vectors. It would be r cosine theta plus r sine theta. But wait, that's the imaginary part. So that guy would be times I. Bro, just write it, times I. Okay. So there you go. That's technically in polar form now, but we don't like the way that looks because both terms have r. So how about you factor out the r? And you get r cosine theta plus, and we move the I to the front as well. I times sine theta. And then, that's a little long. So somebody noticed that a nice way to abbreviate this might be that since it's always cosine plus I times sine, maybe we could just grab those initials, cosine I sine. And then we could turn that into a word, r cis theta. And then that's a really nice shorthand for the polar form of a complex number. And again, don't get caught thinking that cis is some new trigonometric function. It's not. There's still only 6 trigonometric functions. Cis is just a shorthand. It's an abbreviation of cosine I sine. And again, I pronounce it cis. Some people pronounce it kiss. You can call it whatever you like. Except for you, Sebastian. You cannot call it kais. That's not real. That's not an option. Alright, so here I toyed with the idea of doing these problems, and then I said, well, we already did those in class, so why don't I jump to the test review and do some problems from the test review. And this is going to take 100 years, so let's fast forward a bit. Bonk. So I think here I found 3 minus 3i, and I was annoyed because that was the exact same one. So, in aggravation, I decided to make up my own problem. And it was this. It was negative 6 root 2 plus 6i root 2. And I'm going to do this problem 2 ways. I'm going to do it first using the formulas that we just discussed. The r equals a squared plus b squared, or the square root of a squared plus b squared. And we'll calculate the angle using, the phi equals inverse tangent. We'll do all that. But then I'm going to do it again using, that thing, geometry. We're going to do it using geometry. And I'm going to fast forward this a little bit too. We're obviously going to plug those values in, and they go. And to square this, you square the negative 6, that's 36. Then you square the root 2, that's 2. And 36 times 2 is 72. And the other one's 72 as well. So 72 plus 72 should give us 144. And so the square root of 144 is 12. What was I talking about over here, you might be wondering? What I was wondering is, You don't always want to add these numbers together. If they're both the same, at least, would you guys recognize that 36 plus 36 is just 36 times 2? That's how you break the radical down, right? So you might want to jump right to that, and then it's much more obvious that you take the square root and you get 6 root 2. So by adding them, you get a bigger number that you might not even recognize how to break down. So that's just a little trick to think about. Okay, anyway, we agree that our radius is 12. To find our angle, you're going to do the inverse tangent of the imaginary part in the numerator, the 6 root 2, then the real part in the denominator, which is 6 root 2. And I'm ignoring the negative because we're doing the absolute value anyway, right? So you're just getting inverse tangent of 1. An inverse tangent of 1 gives pi over 4, which you guys should know by now. It's 45 degrees. But isn't that number left and up, putting us in quadrant 2? So it's not 45, it's 135, which means it's 3 pi over 4. But that's it. That would mean that that complex number that I just put a gray box around can be rewritten as 12 cis 3 pi over 4. And that's what it looks like in polar form. Okay, now I'm just going to dunk on you guys and do it by geometry. Ready? So, just plot the point in the complex plane. You're going left by 6 root 2, but you're also going up by 6 root 2. Doesn't that mean you're forming a triangle whose legs are equal? But now you should definitely know that a right triangle whose legs are equal is 45, 45, 90. And you should know that the hypotenuse is that leg, 6 root 2, times root 2. And guess what 6 root 2 times root 2 is? It's 6 root 4. But root 4 is 2, so it's 6 times 2, so it's 12. That seems a lot more efficient than doing all that work we did over there with that silly radical and all that garbage. See that stuff? Yeah, that was stupid. Alright, and you know it's definitely stupid, that inverse tangent stuff, because we already know that that's a 45, 45, 90 right triangle. So if that angle's 45, the other angle's 135, and we're done. There's like no math to do if you just use your geometry. So if you're still kind of holding out and thinking, hey, I can get by without relearning these special right triangles, well, you're right, you can get by. But man, oh man, it's a lot faster and it's a lot less work to just draw that silly picture than to show all that other work using the formulas. But yeah, you do get the same answer. Okay, moving on. Alright, what we're doing here is we're basically going the other way. You're being given a complex number in polar form with that cis notation. So to convert it back to rectangular form, just remember what cis stands for. It stands for cosine plus I sine. So just expand it out. And then you can evaluate these expressions, right? You get 10 times the cosine of 2 pi over 3. And the cosine of 2 pi over 3 is, let's see. 2 pi over 3 is 120. Cosine is x, so that feels like negative a half to me. Plus sine is the y, so positive root 3 over 2. And so from here you just distribute 10 onto that, and half, or negative a half times 10 is negative 5. Plus 5 root 3, and I like to put the I in the middle, so 5i root 3. And then you're done. That's your a plus bi form. And that's what it means to convert to rectangular form. So that's it. It would be negative 5 plus 5i root 3. And I don't know what I'm saying right now. It's probably really cool though. Gonna fast forward it though. Alright, so here we have to do operations with complex numbers. You have to multiply them and divide them. And if you had to do it in rectangular form, like I'm about to, then those are both binomials, right? If you were going to multiply that, you'd have to FOIL it. You'd end up with an a times c plus an a times di plus c times bi plus a or d times bi squared. You'd have to remember that I squared is -1 because it's the square root of -1 squared. So that term would become real, and that term on the end would combine with the term at the beginning because it's also real, and the two middle terms would combine. It's it's a whole rigmarole. So it sure would be nice if there was a simpler way, and there is. You would express these numbers in polar form, and then as you see me circling and boxing, literally all you got to do is multiply the radii and add the angles. And to divide, you divide the radii and subtract the angles. So let's go do one of those. Bonk. So these problems were the ones we already did in class, so I jumped ahead to the homework. And I keyed in on 21 and 22. So for 21, we know that z1 times z2 would literally just be the two radii multiplied together. So 5 times 3, which makes 15. Cis, the two angles added together. So pi over 4 and 5 pi over 3. And to do that math, you need a common denominator. So multiplying by 3 over 3 gives 3 pi over 12, and 4 over 4 gives 20 pi over 12, which if you add gives 23 pi over 12. And I think I'm talking now about how 23 pi over 12 is so close to 2 pi, but it's not too big. And if it was too big, then we'd have to map it back, right? Because we always want to use thetas that are greater than or equal to 0, but less than 2 pi. So if you got a negative answer, you'd add 2 pi on until it was positive. And if you got something greater than 2 pi, you would take 2 pi away until you were less than 2 pi. But the 23 pi over 12 is fine. It's not too big because 24 pi over 12 would be 2 pi. So this guy we can leave alone. That's our final answer. All right, then I think I went on to do, oh, what am I doing? What am I doing? Oh, I know what I'm saying here. And it's good stuff too, but it's not relevant, so I'll fast forward. All right, so for 22, they were asking you to do a quotient. I mean, they're asking you to do a product, but I'm going to do it as a quotient just so you can see the other expression. We just divide the radii, and we just subtract the angles. So that's going to be root 3 from number 22 divided by 1/3, and 3 pi over 4 minus pi over 6. So here you multiply by the reciprocal. So you multiply by 3 over 3, and you get 3 root 3, and 3 times 1/3 cancels in the denominator. Here, yeah, 3 over 3 gives 9 pi over 12, and 2 over 2 gives 2 pi over 12, so 7 pi over 12. And that's your final answer. It can't be simplified, so that's it. There's your quotient. Moving on. Oh yeah, so it's time to talk about de Moivre's theorem. And I'm not going to do the warm-up because we already did that. I'm going to talk about some junk nobody cares about. I'm going to point to a problem that we already did, and then talk about how maybe we should do a different problem. And then I'm going to find one. Or I guess I'm talking about the formula here. So to raise a complex number to a power, you're going to end up doing r times r times r times r, which would be exponential. You would end up with r to the power of n. But the angles you're adding, right? So you'd be getting theta plus theta plus theta plus theta. So that would be theta times n. And that's it. That's all of what de Moivre's theorem says, is that to raise a complex number to a power, you're multiplying the radius over and over and over again, so that becomes exponential. And you're adding theta to itself over and over and over again, so that's just multiplication. That's it. So, I'm apparently on the hunt for a new problem to do. I'm unsatisfied with the ones from class, so it looks like I'm going to jump to the homework. And here in the homework, 33 is looking good. So we do, oh boy, what are you doing? Just go do it. Go do 33. Okay, so there's 33. So we're going to do, oh yeah, it wasn't in cis notation, so put it in cis notation just to simplify. Okay, slow down, bro. Yeah, it would be 2 cis 3 pi over 4, and you're just cubing it. So that means you do the 2 cubed. You cube the radius, but then you take the angle, 3 pi over 4, and you just multiply by 3. You just triple it. Typo. My bad. Alright, but from here, won't 2 cubed just be 8? And won't that just be 9 pi over 4? But don't stop there, because 9 pi over 4 is too big. 9 pi over 4 is bigger than 2 pi because 2 pi is 8 pi over 4. So just subtract the 8 pi over 4 to be left with 1 pi over 4. And that'll give you a simpler and final answer of 8 cis pi over 4. JK, that's not the final answer. Because, look up there. They wanted standard form. So standard form means you better take this thing and kind of expand it out again. Remember, cis stood for cosine plus I sine. And so just evaluate those two. Cosine and sine of pi over 4 are both just root 2 over 2. So distributing an 8 onto that would give you 4 root 2 plus 4i root 2, which is hiding behind my face annoyingly. I just realized it. I will now grab that for you and shrink it down. There's your final answer. So 4 root 2 plus 4i root 2 would be the third power of that complex number. Okay, and then finally, here's the lesson that we did today that I didn't really finish. On this page, there's a whole mess of junk. We did this in class where we were trying to derive our rule. So we were talking about the first root of 1, and then the second root of 1, and the cube root of 1, and the fourth root of 1. And I go through and talk about all this again. So in the equation x equals 1, there's obviously just one solution, just 1. And in the equation x squared equals 1, if you took the square root of both sides, you'd get plus or minus the square root of 1. So you get two solutions, negative 1 and positive 1, and both are real. And then, what are you still talking about, bro? Alright, I skipped over x cubed because that was a complicated one, but to solve x to the fourth, you subtract the 1 from both sides, and then you factor it like a difference of squares. You get x squared minus 1, which factors again to x plus 1, x minus 1. And those two factors give us our two real solutions, negative 1 and positive 1. But x squared plus 1 is a quadratic factor that's going to give us two complex solutions. Give me a minute and I'll move my face. Give me another minute and I might scroll down. Yeah, so there it is. So you can see here to solve, we just subtract 1 from both sides, take the square root. That generates another plus or minus, but it's plus or minus square root of negative 1. So we're getting plus or minus I. And so that means we have 4 fourth roots. We have two real ones, negative 1 and 1, and then we have two complex ones, negative I and I. From here I double back to x cubed equals 1. Don't I? Yeah. Okay. And to solve this, we solve it like we did the last one. We subtract 1 from both sides again, but this time it's a difference of cubes, like an a cubed minus b cubed. That always factors down to a binomial times a trinomial. And it's the cube root of this, which is a, and it's the cube root of that, which is b. Then it's the cube root squared, a squared. And then it's the cube root squared, b squared. And the middle is cube root times cube root, so a times b. Then we use the mnemonic SOAP, S-O-A-P, and we did the same sign. So because we were factoring a difference, we put a difference. And a difference, the opposite, becomes a plus. And then AP stands for always positive. So plus, or always plus, whatever it is, but it's plus. But so we can use that now to factor x cubed minus 1. We get the cube root, which, let's maybe not glaze over that. Okay, hurry up. So the cube root of x cubed tells me I'll get an x and I'll get a 1, then I'll get an x squared, and a 1 at the end. In the middle will be x times 1, so x. Binomial, trinomial, still equals 0. Using SOAP, same sign minus, then opposite sign plus, and then always plus. So there you go. So the x minus 1 factor, that linear factor, clearly gives us our real solution, x equals 1. But then that quadratic factor is going to give us 2 more, because we got to end up with 3 solutions. So we're going to get 1 that's real and 2 that are complex. And to find those complex solutions, we have to use quadratic formula. So there you go. X equals negative b plus or minus square root of b squared minus 4ac all over 2a. And everything's a 1, right? B is a 1, A is a 1, C is a 1. So if you make everything 1, then you get x equals negative 1 plus or minus 1 minus 4 all over 2, which gives you negative a half plus or minus. That's square root of negative 3, so that's I root 3 over 2. Okay, so we now have the first root, second root, third root, fourth root of the number 1. And the whole point of this activity was now to go looking for a pattern. So the first obvious pattern was x to the 1. How many solutions was there? 1. When you wanted the square root, how many solutions were there? 2. Fourth root, 4. Third root, 3. So that's obvious. But what I'm about to say is, hurry up. When we solved x equals 1 and there was only one solution, we got our one answer. Come on, put it down. Put down the one answer. And there it was. Treating it as a complex number. Our answer was 1. That's technically complex. It would just be 1 to the right on the real axis. X squared gave us plus or minus, so that gave me 1 and negative 1, both on the real axis. Then, here's where kind of the magic happens. X cubed equals 1 had 3 roots. My real one is 1, which is right on the real axis. But the other two were complex. So they had a real part, negative a half, and an imaginary part, root 3 over 2. So I go left a half, and then I go up by root 3 over 2, which puts a point right there in the complex plane. And that should ring bells. That's 120 degrees, right? If we think about the unit circle. We went left a half and up by root 3 over 2. So that's 120. And then we went left a half and down root 3 over 2. That's 240, right? That's another 120 degrees. So our 3 points are just kind of chilling, symmetrically around the origin. And then x to the 4 really drives the point home. We get our 4 solutions. We got 1, the real number, negative 1, the real number. Then we got I, so I'm 1 unit up. And then I got negative I, I'm 1 unit down. So look at that, it's 4 points, chilling symmetrically around the origin. So imagine a circle. When you had one solution, you get the one answer and then no others, of course. Then you get 2. So you get your first answer, and the other one splits the circle into 2 equal parts. There's 2 solutions, so they're 180 degrees apart. 360 over 2. Now here, imagine a circle connecting all 3. You get your first solution right there on the x-axis, and then they're all symmetrically spaced around, 120, 120, 120, because that's 360 divided by 3. And so I know my 3 solutions will be evenly spaced around a circle. And then lastly, one more time just to really rub it in. If you imagine a circle, you get your first solution, wherever that falls. It happens to fall at 1. But you know that your other 3 solutions will be spread evenly 90 degrees around the circle. 90, 90, 90, 90. So that's it. So this is me rubbing my neck and wondering, I wonder if I can extrapolate this out to all complex numbers, because we were just finding the roots of the simplest complex number of them all, just the roots of 1. And they had that property of, you find the first answer, and then the others are spread around a circle evenly. And of course, well, you can. You can do the thing I just said. You can extrapolate out that this will be true all the time. So I'm trying to find an example. 6th root of negative 64 looks boring, but the 4th root of that thing looks intriguing, so let's do that. So how do you find the roots? Well, I'm about to say it, so let's just say it. One way to find the root is to do the 4th root, but another way is to raise it to the power of a 4th. And if we're raising a complex number to the power of a 4th, then are you thinking what I'm thinking? Are you thinking de Moivre? If you were, then you're thinking what I'm thinking. But unfortunately, de Moivre's only works when our complex number is in polar form. So we're going to need to first convert this thing into cis notation, which means busting out our trusty geometry skills. We're going to go to the right by 5 over 2. Then we're going to go up by 5 over 2 times the square root of 3. And if that ain't a special right triangle, I'll be shocked, because I went to the right by some amount, like n, and I went up to that same amount times root 3. Isn't that the ratio of a 30, 60, 90? You got a short leg and a long leg that's just multiplied by root 3. So call me crazy, but that's a 60-degree angle because this is a 30, 60, 90 right triangle. And call me crazy, but the hypotenuse is the short leg doubled. So it's 5 over 2 doubled, so it's 5. And you're done. If you know the radius is 5 and the angle is 60, aka pi over 3, then you just converted. You don't have to do math. You can use your geometry brain. Don't use that dumb formula. Don't use that dumb formula either. No, I mean, you can, but I promise you, you'll have a much better time if you just actually think about the geometry in your special right triangles. In the garbage. Alright, so grab that guy in cis notation, and you're finding the 4th roots. If it's the 4th root, there'll be 4 of them, right? It's plural. Find the 4th roots, plural. And there's going to be 4. But let's start by finding the first one. And to find the first one, you just take 5 cis pi over 3 and raise it to the power of 1 over 4. So that's what I'm doing. And doesn't de Moivre's theorem say, just take the radius and raise it to that power? So 5 to the 4th. And then it says take the angle and multiply by that power. So you're just going to do 5 to the 1/4 cis 1/4 of pi over 3. 5 to the 1/4 is just 4th root of 5, which can't really be simplified, so we end up with that radical expression. Then you get cis pi over 12. So we did it. We found our first answer. And pi over 12 is half of pi over 6, and pi over 6 is 30, so pi over 12 is 15 degrees. So imagining a whole entire circle, I'm just going to go the 4th root of 5 units out along a 15 degree angle. So my first 4th root is like right there. But you know there's how many 4th roots? Aren't there 4? Well, so I got to find the others, right? We got to find B and C and D. And I went off the screen, but I think I realized it pretty quickly. Not that quickly. Alright, but if there's 4 of them, then 360 divided by 4 is going to tell me that they're all 90 degrees apart. So guess where the other guys are going to fall? So there's my first one. 90 degrees would put the next one there. 90 degrees more would put the next one there. 90 degrees more puts the next one there. It's almost like they're sitting at the corners of a square, right? But there you go. You have just drawn the picture of all 4 4th roots of that complex number. So there's a navy blue one. What's that guy? Is 4th root of 5 cis. Well, what's that angle? We started at pi over 12, didn't we? So you just add on pi over 2. And isn't pi over 2, how many pi over 12s would that be? Oh, I'm writing behind my face. I'm sure I'll realize that really fast. Wouldn't it be 6 pi over 12? So you add it on, you get 7 pi over 12. That's your next answer. In green, who's that guy? The radius would still be 4th root of 5, right? cis. Just add on another 6 pi over 12, because that's pi over 2. So you land on 13 pi over 12. And then finally, I think I turned that purple guy purple, because I love my color coding. Ooh, I made it lavender. That's even better. But the fourth one, that guy down there in quadrant 4, that guy's going to be orange. Would you hurry up? What are you doing? Oh, I guess I'm showing how they're equally spaced. It's pretty good. Good move, Mr. F. Very, very illustrative of what's going on. 90 degrees apart. Just do the last one, though. Come on. Go, go, go. Orange! Realize that you're off the screen? Do you realize it? Do you see that you see that no one can see that? No? You guys can probably bet that we're writing 4th root of 5 cis 19 pi over 12. Put a big black box around it. Still not realizing I'm off the screen. But those are your 4 solutions. The purple thing, the blue thing, the green thing, the orange thing, those are the 4 4th roots. Alright, I realized it. I'll shrink it down for you now so you can see it. Shrink. There you go. Those are your 4 solutions. I'm now going to explain something that I think I ultimately end up not wanting you to actually do. But because we're only finding 4 4th roots, it's pretty easy to literally just list all 4, right? But what if I'd asked you for the 6th roots? Would 6 be too many? Would you start to complain about having to list 6 things? What if I asked you for the 10 10th roots? Or the 15 15th roots? At that point, you would definitely be complaining about having to write me, 10 expressions, 15 expressions, right? So, is there a way to simplify this? And the answer is yes. What am I doing right now? Oh, I'm just explaining that I think to do this I would use the variable omega. If omega was defined as the 4th roots of z, then I could define omega as belonging to the set of all expressions of the form 4th root of 5 cis theta. The only thing that changes is theta, those angles. So just say theta. And then you do this vertical line that says it's the set of all of these expressions theta such that or where theta equals, and then you just go on to define what theta is. So define it, bro. Could you just go define it? So we're saying theta such that theta equals, and we're just going to write an expression. The first value was pi over 12, then we added on pi over 2, right? Pi over 2. And go behind your face, figure it out, move your face. Move your face. Mr. F, move your face. Done. Alright, so we're going to do the k thing again, right? It would be pi over 12 plus pi over 2 k. But k can't just be any integer, or else we'd be getting infinitely many solutions. We literally just want k to be 0 to give us pi over 12. Then we want it to be 1, and then 2, and then 3. But that's it. Those 4 numbers would give us our 4 solutions. So that big long expression there is a way to give all 4 expressions using one kind of compact notation. But obviously if you're only giving 4, then you should probably just give all 4. You would use the notation I just said if you were asking, if I was asking you for the 14 14th roots or the 20 20th roots. But I'm not. If I'm only asking you for, the 3 3rd roots or the 5 5th roots, then you probably just want to list them all. Especially because I want to see you giving me those angles. The pi over 12, the 7 pi over 12, the 13 pi over 12. I'm going to be looking for those actual angle measures. So you better actually list those guys out. Rather than just giving me some expression going, haha, here, this is it, haha, figure it out yourself. No. Don't make me figure it out. You figure it out. But there you go. And round about here the video ends because we're done. That's it. That is how you find the roots of a complex number.